Okay, so today I'm going to introduce network coding gaps, which characterize benefits that you use network coding than you just use like classic routing techniques, right? I will define it shortly. Um, Before that, let's briefly review what we learned like in the last two lectures, which also appeared in this chart. And you will see the results in a new perspective in this lecture. So yeah, in the very first lecture, I introduced what is called network coding conjecture. Yeah, and today we'll see it is saying the network coding gap equals to 1 in this multi-source unicast setting, undirected throughput. And also in the first lecture, we see this result. And also I mentioned this result. This is called multi-party computation, but not in a complete graph. Now you are given a graph G, right? And I claim that we can do it in SQG time, which is sublinear in good behavior graphs. Like for expander graph, it is polygon. Yeah, and also in that lecture, I proved this result that even for a single source like ST unicast, you want to send a bit securely, say if the eavesdropper is listening to at most f edges, and now given the graph is f plus 1 connected, you can always send this bit securely in the diameter rounds, in congested model. And this will gives you a network coding gap of omega n, which is in some graph, if you use classic routing technique, I will define it. It takes, say, much longer, say the diameter of G minus F. Say F is edges eavesdropper controls, right? It forces you to send the information through some safe path. But here you can actually bypass this. That's what we proved in the very first lecture. Yeah.
Okay,
Mm-hmm.
no G is always less than F.
But what I claim is if eavesdropper is taking some is taking control of some subset of edges, if you don't use network coding, you will need the diameter of G minus F. F is a subset of edges eavesdropper control.
Right.
And you will need the diameter of that thing, and that might be linear.
Yeah, but it's still also linear.
This is a gap, sorry. So this is not time. So time, okay, I forgot to rule. Thanks for this. Oh, yeah. Yeah, this is gap, sorry.
What do you mean by gap?
Yeah, like the ratio of the classic routing so like the routing time over the network coding. Yeah, like what's the benefit ratio of using network coding?
Okay, so clarify the concept
Yeah.
correctly. If you use standard coding, you just get diameter of G minus F. And using network coding, you can get constant.
You can just get diameter. D is the diameter of the original graph. You don't need to. You don't even need to know what eavesdropper controls.
Oh, and you're saying that to
This is-
compute diameter of G minus F takes ordinary time, but diameter of G you can just go over it. That's a constant time.
No, this is diameter. D is the diameter.
Oh, it looks like one.
No. Yeah, like there exists some graph. I will define network coding gap. Yeah, okay. There exists some graph that the diameter of G is small, say some constant, but the diameter of G minus F can be large, which is linear. So this is a benefit ratio. Yeah, so
I got stuck on the most stupid part. Your D looks like a one, like a rat.
this is D.
Yeah.
Okay, sorry. Yeah, and also in the last lecture, we learned Ashwini's seminal result of the single source multicast. And if you consider like what you can do in the classic way, that if you doesn't encode the information, you can send the information along a Steiner tree. That you can duplicate information, but you cannot encode. So in that case, So okay, this is a ratio between the quantity, so coding throughput. Oh, yeah, over the tree packing number alpha. Say this is the tree packing. Yeah, this is a coding gap. The max over all the network coding instance that you can think about, right? And this is theta log n for the result we learned from last lecture. So in that setting, coding throughput, recall that it equals to the minimum of t in the set of terminal t, min cut at t, right? Yeah, so this is a theorem we proved from last lecture, and people gave the integrated gap of
so how is there an easy way to see why it's logging?
It's actually directed tree packing, which is called Abelson's tree packing. It's not obvious.
Okay.
So it's quite obvious to show you this is upper bounded by 2 if the graph is underrated. The reason is that by Nash-Williams tree packing, and like okay, there are still some graph trick here that is called splitting off theorem. That given a set of terminals, you can always split off other vertices, non-terminal vertices or standard vertices, so that the graph, the connectivity of the original graph maintains the same, and the splitting of step is like taking two of its neighbor and replace the edge by an edge. Like it's by replacing the edge and you split it off. It's like you pair the neighbors up and you do this step again and again. So in this way, one tree packing will always corresponding to a tree packing in the original graph, which gives you the routing solution, that non-coding solution, and say then it gives you a lower bound of in that in the original graph. And using Nash-Williams, you can show that the connectivity, the gap between the connectivity and the tree packing number is at the most 2. So this is a high level. Okay, so this part, if you lost it, is totally fine because there are some graph techniques involved. Yeah, it's called Nash-Williams tree packing theorem.
What is I?
This is a network coding instance we defined in the last lecture. I consists of okay, G and I. I consists of a set of SITI that I include. Okay, so this depends on the setting. In the single source multicast setting, it should be one source S and a set of terminals T, right? And yeah, that's it. So this is case like it depends on what setting we did. Yeah. So yeah, let's prove them one by one. I want to prove as many as possible. So I think this is interesting. Let's try.
Can you just remind me what unicast multi-class product class?
Yeah, so single source means there is just the one source as B, and unicast there is just the one sink, right? T in B, and broadcast is you want to send to everyone, and multicast is you want to send to a subset B in V. And this multi-source unicast you can write it as SITI. For I in K, there are K of them. And for multicast, SI say each SI send want to send to RI. and there are k of them that are a subset of vertices. Okay, yeah, probably it's yeah, a lot of a lot of notations. But let's start with the easiest one. This omega n is called so multi-source unicast throughput.
So
Yeah, so okay, let me just okay, question.
what is this omega?
This is a network coding gaps. So if I'm not writing anything, these bonds corresponding to the gap in that.
Network coding gap means that if I do something I versus if I code it up. So what's
Sorry?
the gap between these two?
Yeah, like you take the max the instance that maximizes this quantity, right? You want to find the largest ratio that that network coding can value, right? So today we will cover this as a warm up, and this will take a lot of time. And this is simple. So basically, I want to go through the multi-source unicast, which is the most interesting case as there is network coding conjecture in between. Okay. Okay, let's start with the directed graph. I will show you a very simple graph consists of only 6 vertices, and it will gives you a constant network coding gap. This is S1, this is S2. Every capacity are unique. Let's say this is T2, this is T1. Have you ever seen this before? I don't know if I mentioned this somewhere. Okay, then that is great. Okay, then this is an exercise. How do you send a bit, a random bit, like X from S1 to T1 and a random bit Y from S2 to T2? The capacity of every edge is unique, which means you can only send one random bit, which have entropy equal 1. Okay, this is an exercise.
I've seen it before.
Okay, you cannot say.
So simplest is S1 send X and S2 send Y to like to. Oh, it's cross. So like they send the XOR in the middle.
Yes, yes. So yeah, so this is the first magic I saw in network coding. Yeah, this is when you XOR bits together, magic happens. Yeah, so in routing, if you use a routing solution, you cannot hope this, right?
It's all Y, right? Like
Sorry. Yeah, good catch. And you decode Y and you decode X. Yeah, so this is like if you are sending physical commodity, you cannot do this. It's like you have a 1 ounce of mixed like coffee latte. And you're saying, okay, if I have 1 more ounce of milk, can I extract like 1 ounce of coffee from it? Or if I have like one more ounce of coffee, can I extract 1 more ounce of milk? That's not possible. Yeah, but you can do it with network coding. And this gives so in this graph, the gap is 2, right? You can see if you are, yeah, that's what I said, physical commodity, all these two divides into past this edge. And you can boost it to DD. So that's the idea. Okay. This is called butterfly graph. And I just write it in a better way. So that the other verbs. Yeah, so now you want to send it to this guy, right? And yeah, so this is what computer scientists will do, is doing like boosting in a binary way, right? Like binary tree structure. And now what you do is you want to postpone this thing, and you create another butterfly graph in the middle. with coding, you can still send this guy to this guy and this guy to this guy, but with routing, we saw that you cannot, and now you do this. Right, and so that's how you create a network coding gap of 4, and using this magic again and again, you can boost it to linear. Do you see why it is 4? And do you see a network coding solution that send a bit from each guy on the top to each guy in the bottom?
Can you mark the pair?
Yeah, so this is S1 T1, 2, 3, T3, 1, T4. Okay.
So every node is an expert as it is squared.
Yeah, it's so say this here we want it to have x1, x2, or x4, and with the same magic here, I omit the details, but you know how to use it, the butterfly graph to send the corresponding bits, right? And then x1 tells this guy x1 along this edge, and also it knows x1, x4, x2, and it can decode x2. And similarly, this guy knows this, and also x2, and it can decode x1, and same here. Okay. And you just do the same thing again and again, right? That like in the middle, right? Like every routing should need to pass this edge. If you are not doing coding, if you want to go through any SI to any SI to TI, you need to pass this edge. Yeah, that's the observation. And here you create a congest of 1 over n. So here n is 4. In general, it is 1 over n. Okay. So in general, gap will be linear. Okay. Yeah, any question? And this is a form of result.
I was thinking about the broadcast or like a.
This is so today I said we will focus on multi-source unicast. We only care about unicast, which you have k SI TI pairs.
Before the butterfly graph is also like like here it's two channels, so recover X and Y, right?
You can recover both X and Y, yes.
So for this graph, it's here.
Yeah, it's not clear. So here, of course, each TI can decode XI. Yeah.
But you
But you cannot decode everything. Yeah. Yeah. So if you care about multi-source multicast, that's a paper me and Mark did. Yeah, this year it appears in Pod. Yes. Yeah, but today we are not talking about that. It uses more hammer, like locally decodable code. Yeah.
So what did you improve this to? Like,
Huh?
what did you improve this to?
No, this is a like for this the gap is harder to how to say. Okay, it is not an improvement from here because we are studying undirected graph. So it's like all the problems closer to the network coding conjecture are interesting. They all have different behaviors, you will see. And the thing in the middle is like a black hole. It doesn't exist. People don't know anything about it. Okay, so everyone happy with this result for now? Okay. Let me use another board. Okay, let me just say one more thing. What about under? Do we have a gap here? It's not obvious, right? Like because if you turn every edge to be undirected, you can have a routing solution of throughput 1. How? You just observe that there is a cycle, and you split half of the demand here, and so yeah, you send half of the commodity through the left hand side and half through the right hand side, and same for S1. Right. Yeah, you just split your package into half and half and you send a long cycle. Yeah, that's why people doesn't know. Like if you find a gap for under graph, you solve network coding. You disprove the network coding conjecture. Yeah, and now let's go to the paper I want to talk about. It is my Bernard Hepler, David Weiss, and Goran Zublev. So now let's think about another thing, which is now throughput. So until now, I think most of the results are throughput. Only the F-secure model, we have only talked about it once, like what is the run of the algorithm. And now let's think about there is no eavesdropper. I just want to send my bit to the sink. Each SI want to send its package to TI. Okay, and what is the network coding gap in this setting? Could you guess? Although like already written there.
What's the
The completion time if you are sending your package through the graph. Okay, yeah. Let me clarify the model. Good question. So you're given an NDR graph P. So in each run, along each edge, you can send in both directions, say 1 bit. Okay. And now you want to send from SI to TI a package of entropy DI. Say DI bits, they are uniform random bits. Okay. Yeah. So what is the completion time?
Completion meaning that all the sinks need to know.
Yeah, all the things need to know the message of the entropy from its source. Yeah. And yeah, and let's do one more observation to relate this completion time problem to the throughput problem. So it turns out the gap of say if you make the package size turns to the infinity, then the gap turns out to be the throughput equals to the throughput. Limit say C infinity. I'll call this instance, right? And let me just use CI to be the CI. Can I do this? I don't know if there is a better notation. Yeah. Just scale the package. Okay. And the time or
Just scale the capacity of the graph.
I don't scale capacity, so okay. I only scale the instant. There better notation here. Yeah. Okay. Yeah.
But if you don't scale the capacity, then it should take more back, right?
Yeah. So I'll show you like your device C here.
Oh, okay.
Yeah. So see, this is a coding, network coding, like time. Okay. CI. Yeah. So I think this thing equals to throughput of I. So network coding throughput. I need to define better notation, but now let's just if this makes sense, yeah. Let's just but I mean you will see with this connection, a network coding gap of throughput implies a network coding gap of time. Right? So that's why in this chart, everything here if you derive an upper bound here, it turns to an upper bound here. And lower bound here implies lower bound there. So yeah. So that's the reason even people have a network calling gap instance here, it doesn't translate to a network calling gap here because that's lower bound. Yeah. I hope
This is easy to see live stream.
this thing.
Yeah.
Yeah, so good question. Intuitively it is true, right? Yeah, because the formal definition of throughput is a time expanding graph, right? It actually allows you to partition the edge so that you can imagine you have infinite number of time so that you can achieve that throughput. Then recall that in the definition from last lecture, everything you can scale. And then you can always, so this proves your one direction, right? So if you have this thing, you can always turn this into a throughput, which means that throughput is at least this, right? So that proves one direction. Yeah, this is by definition of the time expanded graph and that what we did last lecture. And the other way around,
Yeah, the review is like you can run the optimal throughput out plus something that depends on the delay or the distance. So I see this is really hard.
oh right, yeah. You can round it. Yeah, like for arbitrary epsilon close, right? Like there exists something like you can round. Yeah. Okay, I hope that convinces you. Okay, now let's study the network coding gap of this problem. Yeah. Any question about the setting? Is it clear? Okay, so again, let me first give you a very simple example that shows a constant network coding gap. So now let's think about this K55, right? It's a complete bipartite graph. Minus a matching. I don't want SI to connect to GI directly, so that's it. There are so many edges. Sorry.
You should show the output.
Okay, now
Okay,
okay, now let's create two more vertices and connect them together. Okay. Okay, now let's say each red edge takes 3 times that. Like it's not capacity, it's the time a message past the red channel. And white equals to 1. Okay. So what's the network coding completion time of this graph? Well, this is F1 T1 to F5 T5. Yeah. So each that I just eliminated matching from K55, right? I don't want you to directly communicate to each other. Okay, what is the completion time here?
What are the TIs?
say 1 bit. Like each edge you can send 1 bit, undirected edge. Like you can send in both directions.
So can you do the same thing? Where you export them all onto that side and then.
Yeah, exactly, right? What is the time? It is 1, 2. Yeah, for coding time it is 3. Right, like so here you just XOR everything together, right? And then you decode it because you know every other thing. Okay, and then okay, now let's prove upper bound. Okay, now it is lower bound of the completion time if you're not using network coding. Okay. This is not as obvious as that one. Okay. So we will use at least 15 minutes to get a solution concept here, which is very interesting, and I think that's the main topic today. So how to prove a lower bound on completion time? Could you suggest? Like one thing you might want to do is a generalization of sparsity cut, right? So let's propose, okay? How about this? A 10 to 1. Let's say I specify a subset of edges, and after deleting f, Si cannot talk to Ti, or say the distance from Si to Ti is at least t. Okay, and calculating the completion time is at least mean t. Okay, I need to say the assumption is distance in G minus F as ITI is at least t, right? After deleting F, they are far. And then there are some information can pass the subset of edges F. But in each round, only the volume of F. Let's say for now it's unweighted. Then you need there are k pairs, you probably need k over the size of F round to bypass it. Is this true? So for now, let's think about all the capacity and demand there you need. Okay. Just for simplicity.
One of them is that you completely don't use F. Then you may get T. The other one is sorry, what is K? Oh, K pairs.
Yeah, there are k pairs each with demand 1. So if you're using F, each round you can only use you can only use F to send at most F many information.
Why
And
is
you
it-
need that many rounds.
Can you use like half of each? So.
Oh, because if you are not using this fully, then you need some part of length t.
Yes. Awesome.
Of length t. If you're so this is a full capacity of the set of edges that you're using them every round in a magic way so that you are sending all the information. You use it in a very efficient way. So this is the thing, right? If it doesn't, so if there are still information left that you cannot do it in that many rounds, then you might need t rounds,
Okay.
right? Is this true?
That's like, well,
It is not true.
Do you believe it? But
So this is at least capital T for every pair or something. After moving.
Yeah, I don't think this makes sense. Like F could, you could have like a long path, right? And then you could alternate edges being in F and being outside F, right?
but this is saying the information but that pass you take at least one capacity of F. Say you're sending 1 bit,
Yeah. Oh, I see.
and you have. Okay, so So if this thing is T star, right? In total, you only have that many capacities you can use overall. right? And you need that to be K, otherwise you need information to go through other paths. Is it?
Sounds, it looks correct, but the way you say it sounds like it's not
No, I
correct.
mean, what's so.
Okay.
It's like most of its edges in F, and then it has like a few edges outside of it. I don't, why does that, this is.
So you can use all, like the F to the agent.
Okay, actually, probably I messed things up. Okay, this is probably the correct lower bound for the routing, but not for network coding. You see?
Oh, but not for natural play.
Yeah. I should ask it this way. Sorry. Then do you see?
Is this a contradiction?
Yeah. This is so you just take F to be this edge, and then T will becomes 5. 1, 2,
Oh,
5, right? And then and then K is 5, so this gives a completion time 5. But like with coding, you can do better. Okay, now what is a lower bound of coding? I should ask this. Because if you want to upper bound the network coding gap, you want a lower bound for coding and an upper bound for say the like a general upper bound and lower bound gap, right? So we'll do a LP duality and say, but we still need some concrete lower bound.
but this is if you want to prove upper bound of the gap. No.
The upper bound of routing completion height,
Okay.
which we will see, like you can just run some multi-commodity flow, and that is simple. But the lower bound of the network coding is hard.
Okay.
Yeah. So the next, so this is not a lower bound for network coding, but then can you propose some modification of this? So I will write, and you can think while I'm writing. So. Did I modify anything anywhere?
I do.
Yeah. So now we probably need a pair. Right. So then it is so now I can tell you this is a valid lower bound. So the time, even the coding time. The coding time is at least this quantity. Do you see why? The proof is actually simple, that you can even give the source some superpower, that they know each other's input, which is not allowed in this setting actually. But even if they know each other's input, they still need T time with this bound, right? You prove a strengthened version. Okay, are you satisfied? No, actually I'm not, because this is not tight at all. Okay.
Sure.
So actually what we want is a exact tight version, tight bound, up to polylogarithmic factor, and that's called moving cut. That is proposed by this paper. Probably let me first motivate you by an example of why this is not.
This will not use a tight gap.
This is not tight, and this even so this is a valid lower bound, but not tight. This gap can be polynomially large. I will show you the example right now. So the example is beautiful. These are paths from Si to. So this is S1 T1 blah, 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 to SK TK. And the path is of length square root n. Okay, let's take K to be square root n. Or like up to polylog factor because I need a binary tree on top of that. So for every layer, I create a vertex and I connect everything to it. Okay, this is like one more layer, and I construct a binary tree on top of that. Okay. And what is the completion time here? I mean, lower bound. Like for the network coding. What if you use that one? And what is the correct answer? So if you so let's answer probably the easier question. What if you use A2 to lower bound the like coding time?
And get like more.
You can do better.
Like you remove the top, like half of the layers.
Here?
Yeah, like.
Exactly. That's okay. Let's say the height of this binary tree, it is something like okay, let's say it's L and you just remove all the edges of layer L over 2, right? And what that gives you, okay, now F goes to the 1/4. Because here there are square root vertices, and you are removing the one right in the middle. Up to polylog factor, I just don't care. And then what is the distance after removing them? So each Si to each Tj, you still need you can take some shortcut here, right? But each shortcut, you can this hop you can hop by that much. So now you jump from layer 1 to layer into the 1/4, and you can do it again and again. So the distance is also into the 1/4. So that gives you, and K is certain, that gives you into the 1/4. But this is what the best you can derive from A2. But I would say the answer here should be square root 10. Okay, so now I will show you how.
So if you actually remove the top half of the layers, feels like it's dividing into like echelon 1/4 instances of the originals.
Yeah, there is a recursive behavior here.
Okay.
Yeah. Now. So now let me tell you the answers. A3. So it's a soft version of the cut. So cut is what does cut mean? Cut means for some subset of edges, it just doesn't allow you to bypass it. Right? It just doesn't allow you to cross it. But here is a soft version. I can still allow you to cross it, but you pay more time. Okay. So for each edge, I assign a length here. So it used to be either you can just pass it with say 1 time, or you need say t plus 1 time, which means I am not allowing to pass. This is very slow, right? And now I just remove this constraint. I just what if I just remove this constraint and it can be any integer, right? So that is moving cut. Let me formally state this. Yeah, so now Minkali is a set of LE such that one, the total length increased CE LE minus 1. This is the total length increase. It's less than the total demand. And 2, So anything, so now the distance with LE. So for each pair SITJ, this is at least T. So suppose this, then any coding protocol has mixed span, like completion time at least T. Okay, this is actually a lemma. This is not a definition. I need to. Okay, the definition should just be this. So this is a moving cut, and this is a lemma. Coding time. At least T.
So when you say LD is a moving cut, but the only definition we have here is that LD assigns to each T some integer.
Yeah, that's a moving cut. Yeah, because a cut is you assign it a binary. That's a cut, and you either cut the edge or not. And this is the software.
So how do I understand the first concept? The second one is probably the same as the. Hold on. What does it?
Oh, right. So. Yeah, so let's draw a graph. So this is SI and this is TI, and this graph say this is just the SI doing a BFS, right? And its layer, right? So this is of distance 2 to SI and so on, so forth. And why we need that is we want to capture how many information that you can leap over this step. Okay, you grow a ball at time step 1, all the information is supposed to be still here. And
So
2
this is
still
the-
here.
Sorry, this is the graph before the.
Before, yes,
Oh.
before. Wait, is it before? Sorry. Let me, okay, this is before, but now I want to do a modification. That's what if I change the length, right, of some edge. If this edge now it becomes a length 3. Then actually, yeah, in the so imagine that you have this graph, but not the graph before. This is a modified graph. But actually, information still goes on the original graph. So here, actually, some information it can goes can bypass the length constraint here, right? Because here you are doing artificial things. And how many in total? You don't want that to exceed that many.
Oh.
So that's the idea. So that's the same idea, the same intuition of the A1. So this is like ball growing, and in total, only that many information can be not controlled by this graph. They escape. This information escape. So this is like in total how many information escape from the time growing graph. Okay. Yeah. So that's actually the proof. Yeah. They just formalize this situation. Does this make sense? No. Yeah, I should explain better. Yeah, okay. So now let's just consider one graph, which is a modified graph with this length. And then you do a shortest path from each SI. And then you construct this graph. So this is the first ball is within distance 1, within distance 2, so on and so forth. But there are some edges. Okay, now let's see an edge. It has a length LE. So that means okay, let's consider the information that
Sorry, so what you wrote is there exists LE such that 1 and 2 are.
yeah, there exists LE. So yeah, so this is a graph like this set of LE.
Yeah, okay.
And here I claim like in this graph, if the graph has this parameter, that each edge I'll say that actually.
So the second condition guarantees that no information can reach.
Yeah, no
T,
information.
like using the new length.
Yeah, but how to formally say that at most that many information escape? It is not obvious. Yeah, but probably let me come up with a better explanation next time because I still want to prove something more.
Okay.
Yeah. Yeah, but actually this is the most important. Just give me 1 more minute. See if I. Oh, I see. Okay. So formally, let me just give you a formal proof. So because okay, it's crucial to use a combination of 2 and 1. So let's define AR for R in 0 to T. AR is a set of vertices that there exists I such as distance Si with L Si to V is at most R. So in this modified graph, you have distance at most R to some SI. So for example, these vertices have say are these are in for AR of R at least 2. Okay. And now let's think about like Alice Bob are doing this communication game. Like Alice controls all the SI and Bob controls all the TI. And then let's define that B so BR equal to V minus AR, okay? So then you just consider that this package, this information that you send from AR, okay, for each edge, for each so you just do the normal simulation here, but for the ROM that's in between, that okay, this is UV. So suppose okay, U is a distance of so let's consider this edge that's mean I distance from U to SI or SIU. This time interval that for any R in this time interval, that means I distance V to SI. Here's off by 1.
What's your goal?
So suppose okay, this edge is UV and this is smaller than that, or let's say this is at most that, okay, without loss of generality. And then you consider all around here. And for the message sent in between these round, you just let Bob know this message. Okay. So for this run, you just let Bob know the message sent on this edge. So that's the information escaped. Okay. So it's how much information in total that Bob can learn.
And then you say outside this range, either you cannot reach T or S cannot reach.
Yeah, so either there's still some information you doesn't know, or in that case, right? Like if this should be strictly lesson because there are some information you don't know, then you need to go through at least 10. So that's a kind of idea.
Yeah, when R is smaller than this, it cannot. Then the vertex cannot reach T in time. Wait. Yeah. How do you formalize this?
Yeah. So. Oh. Okay. So okay, this is okay. Let's think about BR is a Bob's view at time R. Okay, and AR is Alice's view. Set Bob growing, and Bob's view are shrinking. So this Bob sees these the information in this ball, and Alice sees the information in this ball, and that's a time slice that information escape, and then besides this, Bob learns nothing from Alice. So does that formalize things?
The run is in the actual coding, not according to the new.
So AR, these are all respect to this metric L.
But the round should,
Round should be actual.
Yeah.
So that's why there are that many information Bob learns from
Right.
this. But besides this, because of our definition, so this is exactly defined so that only this round, in this round, Bob learns something he should has not known. Like, but this is like, okay, because this is a artificial graph, right? So it does learn something it should not know. But that is at most this many.
yeah, I'm trying to see like Bob cannot learn anything further within 2 rounds. Why is it?
So because the definition, so okay, if L equals to 1 everywhere, does this make sense? Bob it literally learns nothing, because Bob is shrinking, right? Bob only sees the information in these vertices. Say if you increase R by 1, it can see less vertices.
Oh,
So it's like, okay, the first round, Bob can see everything except SF. And the second round, you can see these things. But the algorithm only sends this information to its neighbors, and Bob still learns nothing. So if I doesn't modify the metric,
oh,
L equals to 1 everywhere, then Bob literally learns nothing. And now in this virtual communication game,
oh, I see.
I move Bob like with this artificial learn, right? And it actually learns something he should has not learned, which in these time slice.
I see.
And in total, that's the upper bound, the information scaled.
Oh, you get 0, right?
Yeah, thank you.
Thanks.
I think I'm not there is a.
Yeah, yes. This this is yeah, they also prove using natural language like this. Yeah, but I hope you get the idea of like how this virtual communication game captures the information about it. Okay, thank you. Do you have more questions?
But so you can use this to that graph has lower amount of groups and.
Exactly. Yes, I can show you. Yeah. So
And also showing that has lower amount of groups.
yes, this is tied up to polylog. I don't know if it exactly gives 3, but here you should tie up to polylog. So what do you do here is for layer I, you increase all the edges in this layer. Okay, I should order them. Say this is layer 0 to layer L. And for every edge between say layer I to layer I plus 1, right? Then I set LE to be like the increase. So 1 is the base, so the increase is 1 over 2 to the I. So that's the idea. So basically here, you just set this the increase to be say 1. And the second layer, everything increased its length by the half. And here you probably only increase it by something like 1 over square root. But that already suffices. That already say this is a hop. And the length you bypass in this from this view is exactly the probably mess things up. It's like square root n over that. This is so this is only 1, right? So this makes sense. So the length you increased here, should captures that the length you hop in below. So that gives you penalty to hop right. And then the summation of LE is of order square root n, which is upper bounded by the summation of mine. And the distance of every pair now becomes square root n as well.
Makes sense.
Okay, thank you.
I see the table.
Table, yeah.
No, unrelated to the and I think you also talked about it last time, but what is SQ?
Yeah, so SQ formally G to the max of vertex disjoint partition of VI. Okay, so some parameter Q. That you can take Q. So this is a vertex partition. And then mean of say E1 to EQ, max Q and this. E1 to EQ, the congestion of E plus dilation or diameter of max A diameter G VI union EI. Okay, I will now explain. So this is huge. So this is called shortcut quality. So do any of you know Borovka's algorithm to compute the minimum spanning tree? Okay. So given any vertex partition, say this is called a partwise aggregation. So in each part, one need to compute a function, say on the input of the vertex set Vi. So each vertex have an input, and they want to jointly compute a function. And what they can use is they share the graph capacity. Right? All these Q domains, they share the graph capacity. And now what you do is you assign the like these edges. They are not destroyed. So that's why we have a congestion. Say this is a max E that E appears in like how many sets, right? And they share the graph capacity. So this is how I partition the graph to the domains, so that each have low diameter. Low diameter means they can communicate in that much time, and the congestion is like overhead because you need to wait. Yeah, so this is the famous congestion plus dilation routing scheme.
And you do this low form expander because you will have many disjoint paths. So
yeah, exactly. Yeah, so good for good behavior graph, it can be quite low.
and also to sort of recap what we did today. So we first did the HPL thing, right?
Yeah, we first look at this. This is a warm up.
So this is just
Very
a
simple.
butterfly.
Yeah, the butterfly, you boost the butterfly graph.
And
And actually, we haven't fully proved this because we only proved like what we used as a exact lower bound of the condition type, right? It's a almost tight lower bound for the condition type, coding condition type.
right. Okay, so that was for directed graphs, then you moved on to undirected graphs.
Yeah, undirected. This is
So
undirected.
for undirected graphs, you had K5 minus E, and then you had that.
Sorry.
So you for undirected graphs, you had the graph where you go K5, you deleted a matching, and you.
Yeah. That one. That is a small example showing coding can help.
Okay, but then the graph that you took here, that is not somehow.
Yeah, that is not a lower bound. So the lower bound use a very different technique called graph product. It's actually how people prove this network coding gap I mentioned, right? Like either the gap is 1, or if there exists a gap of 1 plus epsilon, you can boost it all the way along to the log to the epsilon.
Okay, let me just
Yeah.
first understand this. So
Yeah.
you do that K55 minus matching thing.
Yeah,
And on that small graph, we kind of see a network coding gap.
yeah.
And then you started discussing this graph, right?
No, we didn't give it the computation, the routing time. We only gave the coding time.
Yeah, so
Also, then you discuss this text.
yeah,
of
that only motivates that we do need some
general purpose.
general upper and lower bound. Yeah, but yeah, for sure, I probably need to say this. So this is only for non-coding completion time, and I believe that if you take that edge, you cut it, you will get So yeah, I do claim that one have a rolling completion time at least 5.
Okay,
So
so,
by this
okay,
bound.
so for this graph, this somewhat 9 bound already gives us 40 bound, right?
Yeah,
It
yeah,
already shows the gap, right?
yeah, already shows the gap.
So,
But in
so
general,
why can't you just blow up this graph?
yeah, for sure. Yeah, that is for the lower bound of the coding gap. So now you achieve a omega polylog k lower bound. That's we have small example and graph product.
Oh, and all this.
All these are for upper
Polylog k is also an upper bound.
an upper bound. Then you do need a lower bound of. It's like the other way. You need a lower bound of the coding completion time and an upper bound on the. And you have a good routing scheme. And there's a one step I missed today, which also takes half an hour. Is that you do need to see the LP of the multi-commodity flow and the cut. And that cut you can translate to moving cut by using another logarithmic factor. And the upper bound you can use a famous result by showing similar to this congestion dilation to show that you can transfer it to a good routing scheme. So that's actually some more steps. Yeah. But this moving cut, the idea itself is clean, so that's why I introduced it.
So this moving cut is to upper bound the routing time, right?
Lower bound the coding time. Lower bound the
Lower
coding time at this t.
Oh, okay. And we'll upper bound the routing time later on to get this.
Yeah, upper bound rolling time. Yeah. So all these here is for lower bounds. Lower bounds is for different things. These two are for coding time, and that one is for non-coding time.
Okay. Thanks.
Yeah, thanks.
Can you talk about the other half of the?
I'm not sure. I only have one lecture left.